This video is the first part of a three-part series that looks at how the form of the Schwarzschild metric is determined using symmetry arguments. In this first video it shows how the metric takes a diagonal form using arguments involving the invariance of the line interval. So given a spherically symmetric distribution of mass m, this mass is not rotating, we seek a metric, g subscript mu nu, that describes the space-time outside this mass. So in the region out here outside the mass, we want the metric that describes it. Now, a static space-time is one for which all the components of the metric are independent of time, t, and the line element ds squared is invariant under the transformation t replaced with minus t. So under time reversal, where t is replaced with negative t, we want the line element ds squared to be invariant. Now, a space-time that satisfies the first but not the second is called a stationary space-time. An example of this is a rotating object, such as a star, neutron star, what have you. That is an example of a stationary space-time, not a static one. What we're interested in today is the static space-time. So we want the components of the metric independent of time, and we want the line element ds squared invariant under time reversal. Okay, so our metric has this general form. This points out it's just symmetric with respect to its two indices. And the line element or interval is ds squared is the metric times dx mu, dx nu, the differentials of the coordinates. Given the symmetry situation, we could choose spherical polar coordinates. X mu is x0, 1, 2, 3, 4, there's four of them, ct, r, theta and phi. Now, stationarity of the metric requires that the derivative of the metric with respect to the time component is 0. And the static nature of this space-time requires invariance of the line element under a reversal of time, so dt will be replaced with negative dt. Now this means this last item, invariance of the line interval under time reversal, means that we can rule out various cross terms in the metric. So under time reversal, negative dt multiplied by negative dt is dt squared, but negative dt multiplied by dr, or one of the other coordinates, doesn't equal the positive dt dr. And to show you what happens to the line element expanded out is ds squared is this component, dt squared plus this component, the metric times dt dr, so on and so on and so on. But under time reversal, we get a different line interval. We get this one here with a negative here. So under time reversal, this line interval is not invariant. And that means we can rule out these cross terms. And we'll see more of those shortly. Also, negative dt d theta does not equal dt d theta, and the same with negative dt d phi does not equal dt d phi. So we can rule out these elements here and these ones here. Now also, how about reversal of the radial coordinate? dr replaced with negative dr. Well, negative dr times negative dr is dr squared, but minus dr d theta does not equal plus dr d theta. So again, there's a number of cross terms again that we can rule out. Also, negative dr d phi plus dr d phi, they're not equal to each other, these two here, sorry. And so these elements in the metric can also be ruled out. Let's just keep going. Remember, it's the invariance of the line interval we want. Now, d theta is this way, negative d theta that way, negative d phi plus d phi. Negative d theta times negative d theta gives us d theta squared, but the negative of this doesn't equal the positive of that, and the same applies here as well. And so we can rule out all these cross terms here, and we're left with a metric that's diagonal in form. We don't yet know what these diagonal elements are, but we know that the cross terms are now ruled out. Alright, so our line element has the form this. Alright, and we need to find the form of the coefficients of this line element. That's these terms here, part of the metric. Now, the rotational invariance of the situation, remember the high degree of symmetry we had, we have a spherical distribution of mass, and we have empty space surrounding it. So the rotational invariance of this situation suggests we use the rotationally invariant quantity r to find the form of the metric. So remember, spherical polar coordinates, X is r sine theta cos phi, y and z in a similar way, and theta here, phi here, so polar angle and azimuthal, and the radial component here. And that's invariant under rotations. It doesn't change its magnitude. Right, so we want to build a line element from a combination of powers of dt, dr, d phi and d theta. Now the metric part of this line element cannot depend on time, as one of the first conditions we had for stationarity, so that only leaves the radial variable r and the angular variables. Now the following form gives us the powers of the variables we seek. So we're seeking a line element of somewhat of this form here. ds squared is this object here, dt squared, and so on, r dot dr squared, multiplied by dt here, sorry, I forgot to mention. Then over here, dr dot dr. That's all the combinations that will result in powers of dt squared, dr squared, and d theta squared and d phi squared. Alright, to see that, the position vector is given by this object here, familiar object. In spherical polar coordinates, that's this. Okay, the basis vectors in the spherical polar coordinate system here, dr is this object, d theta is this one, d phi is that object there, and the unit versions of these, so we now, these three basis vectors are perpendicular to each other, and now we're going to make them of unit magnitude. That's this object here, so we now have the unit vectors in each of the different directions, er, e theta hat, e phi hat, and they're of unit magnitude and they're also perpendicular to each other, so it's an orthonormal system now of basis vectors. Alright, so we can write that again, put that at the top of the page where we can see it. Now our position vector r can be written as r, the magnitude r times r hat, which is a unit vector in the r direction, a unit radial vector in the r direction. Right, we can see that down the bottom here, r dot dr will give us r squared. Now dr, we can expand that out in terms of the basis vectors, dr, and so on, using the chain rule here. There we go. And writing those out, replacing dr, dr and dr d theta, dr d phi by the appropriate basis vectors. Here we go. Gives us, and then we can replace these by their unit basis vectors and a factor. For instance, e theta is replaced with r e theta, so we get r d theta e theta hat. And over here, e phi will give us, we can replace with r sine theta e phi hat. There we go, that object there. So that dr dotted with itself, dr dot dr will give us dr squared plus this familiar object from solid angle from spherical polar coordinates. And we've seen that r dot dr is r dr. You can see that. This object here dotted with this object here, r hat, er hat, the unit vectors, magnitude 1, they drop out and we're left with what become 1, and they leave us with dr r, so that's what we get there. Alright, next thing over, so here we go, here's our line element in this form here, as we saw earlier. Expanding that out now, because expanding out in the brackets r dot dr squared, dr dot dr gives us all of these objects. Alright, now let's collect like terms, so dr squares, let's collect all dr squareds. Here it is, dr squared, this cr, that. This cross term here, dt dr, here it is. Alright, and dr outside of this angular part here, times r squared. Now we're going to absorb the factors of r into the coefficients so that our new coefficients become a, which is unchanged, but b becomes b dash, c is replaced with c dash, d dash. Okay, and just to point out here, our new c dash is all of this, that becomes c dash, and d dash becomes all of this. Alright, so our new line element is ds squared, is that object here, this one, and there we go. Let's keep going. Let's define a new radial coordinate. R bar squared is d dash of r, and when we do that we lose the d dash, that's replaced by r bar squared. Now we're going to introduce a new time coordinate t bar, and and that's going to be given by c dt bar is some function f of r bar times this object in here, which is just this, okay, sort of this. And now we're going to square it and solve for a and b dash. So squaring both sides, we get c squared dt squared here, f squared, all of that expanded out, which is just the square of this, that squared plus 2 times those things multiplied together plus this bit squared over here. Keep going, divide through by f squared to free up the right hand side here, and then this bit, final bit here, bring that over to the left, and we're left with something that looks like what we had on the previous page. Okay, now next thing through, let's divide through by a, and we'll end up, and we'll take this bit over on the right, we'll put it on the left hand side just to make the whole thing easier to look at. So I'll divide through by a, that'll give us this object, and this bit over here divided through by a gives us this over here. Alright, and then we'll multiply both sides by -1, and so that all becomes negative there, and these terms over here become, this one becomes negative, that one becomes positive, and we'll see how we use that in a minute. Next note, so our line interval becomes, or line element becomes, ds squared is this object, negative out front, plus this object here, plus that. Okay, now let's just tidy this up, because we're almost there, we've almost got the form we want. Now define a bar of r bar is this object here, so this bit here becomes a bar, and b bar becomes all of this here, that bit there, except for the dr bar squared. Alright, now let's substitute that in, so we've got negative a bar, that, plus b bar, all of that, plus the solid angle part over here, and look at that, we now have a diagonal metric. No reason to hang on to the bars anymore, we can drop them, it's not necessary to do it, they're merely labels. So the line interval, or line element, is now in diagonal form. Here it is, now in diagonal form. And so our metric is given by this. This is our metric. And our next job now will be to find out what A and B are. Alright, now, very far from the source mass, a long way from the source, we'd expect these and these to go to 1 in the limit as r approaches infinity. So this metric approaches the Minkowski metric in the limit as r goes to infinity. So a long way from the source mass, we expect this to go to the Minkowski metric, so they should reduce to -1 here and 1. Right, now from the weak field limit, we have on a previous video on the weak field limit, general relativity and the low speed weak field limit, we had this object here we found in the bracket on the right, 1 plus 2 phi on c squared, that bit there, where phi was the familiar potential function for 2 point masses in Newtonian mechanics. And let's say we'll take a source mass, a test mass of 1 unit mass, 1 kilogram. Here we go, unit mass, so m goes to 1, and our potential function becomes this object here. Substituting that back in to what we found on the previous page, and we can say that a of r is 1 minus 2 gm on c squared r. So our metric is now this object here. And we've yet to find b of r. So in the next video we'll determine the form of b of r.